Alright guys, how's it going? Some of the more intriguing and for sure more technically interesting videos of mine were my 2-year-old AMD The Master Plan videos, Part 1 History, which was mostly about AMD's semi-custom strategy and their game console dominance. And Part 2, The Future of Gaming, was mostly about how, in the future, multi-chip packages will rule over monolithic chip designs. And back then, from my perspective of a gamer, the obvious course for AMD was to employ this technology in gaming. And with hindsight, that was pretty naive of me. AMD, of course, did the smart thing and went after Intel's gigantic CPU market instead. Ryzen and the multi-chip EPYC and Threadripper CPUs were born. And the last video I made on this subject was the EPYC Master Plan, where I introduced the idea of chiplets. In other words, instead of simply using multiple smaller chips, the plan was now to break down whole chips into even smaller parts. And the idea for all of these videos came from a couple of research papers I read back in 2014, 2015. And those were Network-on-Chip Architectures for Silicon Interposer Systems, a research paper by Natalie Enright-Jerger, AJ Kumar Kannan, Zemo Lee, and Gabriel H. Lowe. And 3 of them were back a year later with Enabling Interposer-based Disintegration of Multi-Core Processors. And I guess what makes sense for the video would be to explain exactly what a silicon interposer is. A silicon interposer is a large slab of silicon, which is used to integrate other pieces of silicon. What you're looking at here is AMD's Fury X. This is the Fiji die, a very large GPU, 4 stacks of HBM1, and this part here is a silicon interposer. And here we can see one annotated. Fiji was larger than 586 square millimeters. Fiji die was in fact 596 square millimeters. And the silicon interposer has a huge die size, as we can see, 36 millimeters by 28 millimeters. The interposer that AMD used for this was 1011 square millimeters. There are 1 or 2 differences though. As you know, a GPU is filled with transistors and will generally be fabricated on the very latest manufacturing technology, because performance and power is critical. A silicon interposer, on the other hand, we are mostly talking about a dumb block of silicon. And so these are generally manufactured on older processes, for example 65 nanometers, and the reason for that is simply cost. It would be far too expensive to manufacture such a large slab of silicon on a new process. So using an older 65 nanometer process would get you better yields at a much cheaper wafer cost. 65 nanometer wafer today maybe costs $600 or so, I'm not entirely sure. And if you look at a die yield calculator, using a width and height of 36 by 28, and due to the much older process, we would have much lower defect density. I've gone with 0.02 defects per square centimeter here, but that would give you 34 good interposers on this one wafer. And from the kind of costs that I've seen, a silicon interposer today of this size would cost maybe $20 to $30. It's going to be somewhere around there. So that's exactly what your silicon interposer is. Any foundry will be able to provide one of these on their older 65 nanometer nodes. And initially, the idea of the interposer really was in order to integrate memory much closer to the die and at high bandwidth. So with Fury X, AMD introduced 2 new technologies really, a high volume silicon interposer and high volume high bandwidth memory. People wondering why Fury X and Vega do cost quite a lot of money. When you're doing this, there's simply no way to avoid high costs. But here's where it gets a little bit more interesting. Every interposer we have seen up until this point has been what's known as a passive interposer. And by passive, they mean that there are no transistors on the interposer. This is a 65 nanometer slab of silicon. CPUs were 65 nanometers not so long ago. Something like a Q6600, in fact, was a 65 nanometer chip. So there's nothing stopping the interposer being used for logic. But up until this point, with Fiji, and even with NVIDIA's GP100 and V100, all current interposers have been passive, and by passive they simply mean there are no transistors on it whatsoever. It has simply been metal routing. For example, here we can see here, metal routing here between the GPU and between the logic die which connects the HBM. And here's another view of an interposer from the first paper. In this case, the white area is interposer, and the grey area would be some kind of chip, in this case a CPU, with memory at either side. And again we see the metal routing connecting the CPU to the RAM. And we have all of this potential going unused until the authors decided to extend the network on chip to the interposer as well. Now, extending the network to the interposer does mean putting logic onto the interposer. You're going to have routing switches, you're going to have repeaters. And as we just discussed, on an interposer, such a large piece of silicon, the addition of extra logic could cause a dramatic reduction in yield. But on a yield analysis of a 24x36mm interposer, which is a little bit smaller than the one they used on Fiji, which was 28x36, but this one was 864mm squared. Along the top is different defect rates. We would simply be concentrating on the leftmost column here, as this would be an older process. And down the left column we see 4 different levels of active transistors. So in the first example, the passive interposer, interposers that simply have metal routing, we see a massive 98.5% yield rate, even on that huge slab of silicon. The reason for this is really simple. The vast majority of that interposer is just a slab of silicon. It doesn't matter if a defect hits it. You could only kill the interposer by hitting one of the metal roots. Fully active, that would be the entire interposer filled with transistors. Even with that, the yield rate was still 87%. But the authors discovered that for their purposes, placing the network onto the interposer, they could do this while only requiring 1% of the interposer to be active, and even erring on the safe side with a massive 10%. As we can see, the yield rates barely change between active 1% and active 10% transistors. All these other numbers are simply worse yield rates. And in fact, even at terrible yield rates of 2,500 defects per square meter, 10% active interposer would still have over 90% yield. And in fact, if you just go back to the die yield calculator I used earlier in the video, even these interposers at the edge, with the edges kind of chopped off, the chances are all of these would be absolutely fine to be used as well. And even the one showing up as defective would likely be absolutely fine too, simply because the defects will be hitting something non-critical. So hopefully that explained that part. We moved on from the passive interposer at the bottom here, and we now have an active interposer with a network on chip running on both the CPU and the interposer. And in the paper NOC Architectures for Silicon Interposer Systems, they took a 64-core CPU chip and stuck it on an interposer along with some memory. The authors employed a conventional mesh-like topology covering the 64-core die and a concentrated mesh on the interposer layer. So 2 different topologies, and what was interesting here was that all the core-to-core coherence traffic, that is traffic between all the cores on the CPU, that was handled by the CPU dies portion of the NOC. However, all the traffic going to and from the memory goes across the interposer. And for requests going to memory, the NOC forwards the packet vertically down to the interposer layer at the first chance possible. So core-to-core communication handled by the CPU portion of the NOC, with all the memory traffic going across the interposer. But now going back to the paper, enabling interposer-based disintegration of multi-core processors. So they had this entire system, this 64-core CPU chip. What they then did was disintegrate this 64-core CPU into 4 16-core CPUs. Now, the main reason for doing this is cost. And this is something I have talked about very many times. In a nutshell, smaller chips get you higher yields and therefore more good chips on a wafer. In this example, the 64-core chip was actually 297 square millimeters. That's the one monolithic 64 cores per chip. The 32-core chip was half the size, and because of this you get more chips per wafer. You get more than double because you can fit more smaller chips around the edges of the wafer. So even though you would need 2 32-core chips to equal one 64-core chip, because of this higher yield value and because you get more chips on the wafer, overall you would still have 19 more good system on chips per wafer. And if you move down to 16 cores per chip, as in the main example, you of course get very many more chips on the wafer. And even though each package would require 4 chips, because the yields are so much higher and because you get so many more good dies on the wafer, the number of good system on chips per wafer has now risen to 195. So in effect you would get 20% more CPUs from the same wafer when using 4 16-core chips compared to 1 64-core. And this here is the main reason for disintegrating a monolithic chip into smaller chips. So why would you not do this? Well, one of the reasons for why you wouldn't do this is that when you split one chip, you also fragment the network on the chip, and this decreases performance as the core-to-core messages between chips must now route through the interposer. All of this would have been one connected network. But now when the chips need to talk to each other, CPU to CPU, in any direction, they now need to go through the interposer in order to do so. So it looks like a trade-off. A large cost benefit at a reduction in performance, mostly coming at the cost of additional latency. But is it really that simple? Are there any more benefits or drawbacks from disintegrating these large monolithic chips into multiple smaller chips? And as noted, they did disintegrate this 64 chip into 32, 16, 8 and 4. We already know that the smaller the chip size, the more you get on the wafer, the better the yields are. The overall number of good final packages that you get increases. But there is another, perhaps less obvious, major benefit. And looking at this chart, on the y-axis we have the average number of 64-core systems per wafer, with clock speeds on the x. And as we can see, the black bar, the monolithic 64-core chip, we already know you get less of them per wafer. But not only that, 64 cores on one chip, that entire chip is only as good as its slowest core. So it doesn't matter if 63 of them can do 2.2 GHz, if the 64th one is only capable of 2 GHz. The entire chip would have to be sold as a 2 GHz chip. That is an oversimplification, but one that's easy to understand. So when you have multiple smaller chips, where it gets really interesting is when you sort these 16 quad-core chips. Going back to the yield analysis, remember you have 3,391 of these quad-core chips on that wafer. They're very small, obviously. We can see they're only 18.6 square millimeters per chip, so more than 3,000 on a single wafer. And obviously when you have so many chips and only 4 cores, you have a much higher chance of getting 4 very fast cores on the same chip. And this is what is known as binning. So what this means is the average gigahertz dramatically increases as soon as you sort these quad-core chips, with an average around 2.4 to 2.5 gigahertz. Remember, this is just a spread of the number of 64-core systems. So the average gigahertz has moved from around 2 gigahertz for the monolithic 64-core chip up to 2.4, 2.5 gigahertz for the 16 sorted quad-core chips. Possibly even more importantly though, the top end has dramatically increased. The fastest 64-core monolithic chip they could get was 2.3 GHz. However, with speed binning, the very best 16 chips they could get off 100 wafers allowed them to create a system on chip at 3.1 GHz. That is 35% faster. The same architecture, remember, 35% faster clock speed simply by binning the fastest chips all together onto one system. Now, it should be said, in one way this is best case scenario here, because they have used 16 quad-core chips. As we know from AMD's EPYC, they are using 4 8-core chips. So this average speed distribution will not be quite so dramatic compared to what we see with EPYC. With further disintegration, we see that the speed benefits become very, very large indeed. But what about the performance hit, the latency? Well, as you can see here, there's a pretty dramatic increase in latency. This chart actually normalises cost and message latency, but if you just ignore these grey lines and concentrate on the average latency, we can see the monolithic 64-core chip, of course, has a lower latency than the 32 cores, 16, 8 and 4. This is just what you would expect, as the more you fragment the network, the more potential bottlenecks. So no great surprise there. Average latency of course does increase as cross-core and cross-chip communication increases, and this image shows it pretty well. Now, we heard about the mesh network topology last year when Intel released their Skylake X architecture. One of the big changes was the move from the ring topology to the mesh topology, and this is basically what a mesh looks like, and next to it is a concentrated mesh. Looking over at the left here, the monolithic 64-core chip on a 2D mesh and the link utilization. It's everything you would expect to see in a monolithic chip. All of the links are utilised at about the same rate. However, when you move to 4 16-core chips on the same mesh, this same 2D mesh here, we see a dramatic increase in utilisation along the middle links. And looking at the concentrated mesh over the 4 16-core chips, it is a very dramatic increase. And in fact, the outside links barely get utilised as so much of the traffic tries to come through the middle of the network. So what is causing these traffic jams in the middle? With the monolithic 64-core chip design, on the 2D mesh, all of the core-to-core communication stays on the chip, whereas all the memory traffic, these blue boxes on either side, both in the mesh and the concentrated mesh, all of that network traffic goes on the interposer, and that is why the link utilization remains very similar. However, as soon as you disintegrate the 64-core chip into 4 16-core chips, whenever a core from one chip needs to communicate with a core on another chip, it must do it through the interposer because there are no direct links. So if there is also memory traffic at the same time, in the case of the mesh again, if there's traffic travelling from memory to one of the cores and also data travelling from core to core, this causes causes a traffic jam in the middle, and this is especially bad in the case of the concentrated mesh. So with this in mind, the challenge seems fairly simple. How to reduce link utilization, latency causing traffic jams by changing the structure of the network on the chip. Well, next up they tested the double butterfly and the folded torus topologies. Same again, you've got the 4 chips and you've got your memory channels down the side, but in both cases we see the network topology has been dramatically altered. Moving on from that, they then tried misaligning the topologies, an example of which we can see here. If you've got your left chip and your right chip, first of all on a perspective view, and then the same chips in a cross-sectional view, in the first case we have a normally aligned topology. Each circle is simply a router on the chip and on the interposer, but what the research discovered was that by misaligning or shifting one of the interposer routers to in between the left and right chip led to a reduction in latency between the chips. And they tried a misaligned folded torus on the X and the X and Y, and they also tried a misaligned double butterfly on the X, before at last they came to the ButterDonut and then finally the misaligned ButterDonut topology. And here we can see the entire table of the tested topologies: the concentrated mesh, double butterfly, the folded torus and the ButterDonut, and also the misaligned versions of those. The number of nodes would simply be the number of routers. Generally speaking, the less of these the better, as these are of course active transistors using up a little power. The fewer links and the lower the diameter of the links the better, and those should combine to an average number of hops. And the more bisectional links, the better the chip-to-chip, side-to-side communication should be. The misaligned ButterDonut won out in just about everything, narrowly losing out in the number of links to the misaligned double butterfly. However, given that the average hop was lower, the misaligned ButterDonut won out in the end, the lower latency from the average hop being more important than the number of links. Now, many benchmarks were taken, far too many to cover in this video, but I will of course include the link to this paper in the video description. Looking at this chart, latency on the X and the fraction of all packets on the Y axis, we can clearly see the ButterDonut wins out, with the concentrated mesh falling far behind. This was a system with 4 16-core chips. But possibly the single most interesting thing to come out of this research was this. 2 charts with the average packet latency on the y-axis, but this time with chip size on the x-axis. And instantly we see that both the mesh and the concentrated mesh perform much worse than the more exotic topologies like the folded torus and the ButterDonut. Obviously with latency, lower is better. But what was really interesting was, in all cases, apart from the mesh topology, latency was actually worse with the monolithic 64-core design. This was very interesting and may well be why Intel decided on the mesh topology for Skylake X. But on all other topologies, the average packet latency actually increased between a chip size of 32 and a chip size of 64. In the left chart, all of these topologies were normally aligned. In the right chart, we have the misaligned versions, and we can see even lower latencies, however a quite dramatic increase in latency between a chip size of 32 and 64. So performance actually improves, moving from a monolithic 64-core design to a 32-core design, and continues to improve down to a design with 4 16-core chips. And what's more, there was a very, very small drop-off when moving to a chip size of 8. 8 chips with 8 cores, and pretty much the same latencies as the 16-core versions. There is an increase by moving to the chip size of 4. That would be 16 4-core chips, but really you're talking the difference between 26, 27 in latency. It should be pretty clear that the misaligned ButterDonut allows for very large-scale disintegration of monolithic chips without severely harming performance. And finally, moving on to the conclusion of what is a truly fantastic paper, which introduced the concept of minimally active interposers as a potentially practical, cost-effective way to build network-on-chip logic on the interposer, which, while examining the traffic impact of chip-to-chip traffic across the interposer, led to the development of the new concept of misaligned network-on-chips, which then led to the creation of the ButterDonut topology. The combination of these contributions showed that the performance impact of multi-chip interposer systems can be addressed, leading the researchers to conclude that interposer-based disintegration is a promising approach for building future system-on-chips. And what should be pointed out here is, of course, none of this would have been possible without the interposer. We know that Intel has EMIB, the embedded multi-die interconnect bridge. And many times, in fact, I have said that this looks like a very good packaging technology. However, we can see that EMIB is a bridge. It does not envelop the chips within a package and is therefore unlikely to be viable as a network-on-chip solution. And we've seen with EPIC that current generation EPIC is using the organic substrate, linking the chips via Infinity Fabric. So no interposer there, at least not yet. And we all know what happened with Ryzen's latency. Core-to-core latency very good, even across the same CCX, but latency between CCXs was actually very poor. The question here could be, what could we expect from a change to the misaligned ButterDonut topology when switching from the organic substrate to a silicon interposer? Right, so to finish this one off, it's been pretty technical and covering topics that I haven't really gone over before, and one or two topics that I'm perhaps not that well versed in myself, but hopefully it was all reasonably easy to follow. For me, one of the most interesting aspects of it was the increase in clock speeds when disintegrating that 64-core chip down to 16 4-core chips, just by the ability to bin the better chips in faster packages, the exact same silicon, the exact same architecture, and yet a 35% increase in clock speed simply through the ability to bin better. And we've seen that the active interposer is not any kind of drawback. Interposers will always cost a certain amount simply due to their huge size, but in the case of these server CPUs and even high-end desktop CPUs, another $20, $30, it is absolutely nothing. And the solution to the latency problem appeared to be better topologies. We're using a network on the chip itself or on the interposer, depending on where the traffic was coming from and going. And the misaligned ButterDonut topology, which the researchers found to be the best overall solution, appears to be dramatically better than conventional meshes that we see in, for example, Intel's Skylake X. It's worth pointing out that this paper was late 2015 and Intel launched Skylake X with the mesh topology in the middle of 2017. There is of course a delay between research and actual product, but it was interesting for me to see that the latency of the mesh topology was one that was better with the single monolithic chip, whereas all others, even the concentrated mesh, perform better with 2 or more chips. And it's clear that I've been all in this whole chiplet thing for a very long time, 2 years in fact, all the way from the master plan to the EPIC master plan. So it may not come as any surprise to you that my speculation would suggest that we may just see, with AMD's upcoming 7nm EPIC CPUs, we may just see it on an interposer rather than the organic substrate. If we do see that, we can be fairly confident that we may even see more than 4 CPUs per package. Now obviously I heard a previous rumour of 5 chips on the package, 4 core chiplets and 1 no-core chiplet. I have subsequently heard a rumour of 9 chips on a package, which would certainly seem to necessitate a silicon interposer. As always with these things though, we simply don't know how far away it is. Chiplets are coming one day, whether that's one day at the end of this year, or one day at the end of 2019, or maybe even one day in 2020. For those of you wondering when we're going to see this on graphics, I'm going to leave that one for a future video. I'll catch you later guys.